All right, chapter 11, section 2, reflections. We're still in this chapter on transformations, and again, just a little brief review. Transformations are basically movements or changes from one figure to another. And the value here is that if I can show that the dimensions of some object being moved to another, if it is a rigid motion transformation, which those are terms that we learned in section 1, the nice thing there is that then I don't have to worry about remeasuring things over and over again. I just know that once it's moved, it's a copy and paste version of the original. Okay, and so this transformation is simply a movement. In section 1, we talked about the simplest of those movements, which was a translation or a slide where every point on an object moves the same distance and same direction. In the second one, this is one that arguably you're just as familiar with or more familiar with than translations, and it's called a reflection. We're most familiar with this, obviously, with looking into mirrors, and the effect is pretty much the same. So the formal definition is that a reflection is a transformation that reflects every point of a figure across a line of reflection that we'll call a mirror, for lack of a better term, but the line of reflection mathematically is essentially our mirror. So that the distance from the original point to this stands for line of reflection, LOR, line of reflection, so that the distance of the original point to the line of reflection is the same as the distance from the line of reflection to its image. That is a lot of words, okay? It's actually a very simple concept. And again, one that's very easily accessible even in your bathroom mirror, okay? It's this idea that if I have some mirror or line of reflection, whatever object is on one side, the original object, like say where you're standing in front of a mirror, the distance from you to the mirror is the exact same distance from the mirror to your image, right? So that if you were to walk toward the mirror, your image would also appear to walk towards the mirror, towards yourself, right? To the point that even if you were touching the mirror, like you high-fived the mirror, it would appear that your image was also high-fiving you back. Okay, a very important concept there. And the reason why they call it a line of reflection as opposed to the mirror is because when we think of a mirror, we think of actually like a solid object. One thing that can happen in mathematics is that something can reflect on itself. So the mirror could actually pass through an object, the line of reflection. And it's tough to imagine that because a mirror is an actual physical object. It can't like actually cut us in half, sort of thing. So in this case, we'll keep calling it a line of reflection, an LOR in short. But as an object gets more complex, the reason why this can kind of be a trap is because reflections are actually a little bit more complex to try and visualize. And a lot of people make the mistake of just trying to they overthink it or underthink it, depending on how you think about it, about like where the object or the image will be on the other side of the mirror. And it's reverse, kind of something that kind of bends the mind is that if you were to go into your to look into your bathroom mirror and raise your left hand, your reflection, your image, would actually appear to raise its right hand. That's the kind of fundamental thing about a reflection. It reverses things on the opposite side. It's a pure mirror reflection of whatever's happening in the other. And try it. Like look in a mirror, put your left hand up, and then notice that if you were to be the reflection, it would be your right hand actually that would go up. And it's kind of it bends the mind. And that kind of concept is why some people struggle with a more complex object being reflected over. Okay, it's this idea that it's tough to see that mirror image on the other side. It's just for whatever reason, it's just tough to bend your mind around it. The simple mathematical way to attack this is that every point it's just this same distance to the other side. So right here, this original point is 2 units away from the mirror. Straight across, it's going to be another 2 units to the image. Okay. Another thing just to talk about mathematically is that the distance from some original object to the mirror, it's got perpendicular distance. So this is a vertical mirror. The horizontal distance to that vertical mirror is perpendicular. So it's 2 units away. And if 2 units along that same line is going to be taking me to the image, it wouldn't bend over here somewhere. Okay, not unless it was a funhouse mirror or something. But again, kind of going into a more complex object, again, if this was point A, 2 units, 2 units. All right, there's A prime. If that's point B now is 4 units away. And then so that means 4 units away to get the image of B. And just as more complex as the object gets, that's exactly the process that you'll go into. Just go point by point. I know it's going to be tempting to just be like, one of the more common mistakes here is they'd say like, all right, well, there's that corner. Now I'm going to draw the triangle over here because that's exactly what it looks like. That would be a translation, like just sliding as it is. We can see with the reflection, it reverses the image. All right. So it's a very simple concept. It's just matching a distance to the other side of the line of reflection. But trust that process, because if you're trying to do it in your head or trying to visualize it, it can quickly become confusing for some people. Anyway, so let's move on into our lower half of the notes here. Before I jump into these examples, I wanted to talk about what's here in the margin. So in the margin, we have some coordinate rules for reflection. So these are actually very valuable shortcuts, a little cheat sheet for us to work with when it comes to reflection. These first two, I don't know that the actual conversion here is any faster than just doing the work on the coordinate grid yourself or just counting the squares. Horizontal and vertical lines will be mostly what you deal with when it comes to lines of reflection, but these two in particular. So make sure you circle these, star these, draw your attention to these in your margin, because these two right here are going to be highly valuable. And the reason why is because they're diagonal lines of reflection, diagonal mirrors. Why does that matter? Because it's easy to count squares perpendicularly to a horizontal or vertical line. You're just counting squares away. Not as easy to do that with diagonal lines. In fact, you'd have to create a perpendicular line with that mirror, and that's a whole process that's a very annoying thing to do. So these conversions here will come in very valuable. And what they simply break down is this, is you'll be told you have a line of reflection that's, say, y equals x. That's this diagonal line. It's the positive one slope line that goes diagonally through the coordinate grid. And so that would be what the mirror looks like, the line of reflection. And this is what this conversion means. Like for every coordinate point I have, let's say I had a coordinate point like 5, 3, and they were like, all right, reflected over this mirror, this line of reflection. Well, if I have 5, 3, this is how I convert it to where its image would be. So I basically just swap the x and the y coordinates. So if I had 5, 3, my new coordinate would be 3, 5, and that would be its image. Okay, so again, nice little cheat sheet here for when I have this mirror. This is what we call the diagonal, the negative diagonal rather. And we can see this is what that line of reflection would look like, y equals negative x. Again, the negative diagonal. And this is what happens to the coordinate. So again, if I had some coordinate point 5, 3, not only would I swap them, but I'm going to flip each sign. That's what that negative means. So 5, 3 would become 3, 5 in reverse order, but I'm going to make it negative 3, negative 5. Okay, so that's how you would use this cheat sheet right here. These both work for the x-axis and y-axis specifically, but it frankly, for these two, it's just as easy to just count your squares away, because again, with a coordinate grid, as you can kind of see on my graph paper, these blue lines are perpendicular to each other, so you can just count perpendicular how far away, kind of like we did here. This would be the equivalent of like the y-axis and then counting points away. All right, so let's jump into a couple of examples. Again, like in the last section, normally I would do this on a whiteboard, but quite frankly, it's just as easy to do this on my solution sheets that are available on Google Classroom as well. So in this first example, we are given an A and B thing to perform. We're given some triangle. And again, on Big Ideas, you're going to be asked to graph these. I went ahead, for time's sake, went ahead and graphed those out for you. There's our triangle ABC. We're asked to graph the triangle and its image after the given transformation. We're given a movement in each of these cases. Both of these, along with our section, deal with reflections. And here's another thing to put in your margin. I put this in the margin on our solution sheets, but you got some space up here. My suggestion, do this. This is something we've talked about, this right here. This is something we've talked about in previous chapters. particularly when we dealt with graphing y equals mx plus b lines and linear functions and all that kind of stuff. But for instance, here, you're going to be given reflection over something, and they're going to give you an equation. This is a linear equation, actually. Okay, this is a line that you're going to be given, a mirror that you're going to be reflecting the object over. And more often than not, you're going to be given either a vertical line or a horizontal line. The two exceptions to that is you'll sometimes be given one of these two things. These are both the diagonals, and it'll be one of these two. There are obviously an infinite number of other lines that can be drawn, but for the sake of just the practice of doing this chapter and the work, these are pretty much the only scenarios you're going to be dealt with. So it's one valuable thing to put in your margin is this little hint. If ever I get x equals some number, that's a vertical line. Okay, so x equals 3, it's a vertical line at positive 3. That's what that represents. Conversely, if I have y equals some number, like in this other example, if I have y equals some number, that's a horizontal line. And in this case, it's at positive 1, so I'd go up 1, there's my horizontal line. Okay, so just be careful with that. That's just a little shortcut. You will be seeing that several times over in this section's assignments, but that's what both those mean. It could be valuable to put in your margin just to remind yourself what happens when I get this sort of statement. Anytime you get a reflection, your line of reflection will be a linear equation. These are both lines. It's just valuable to understand that that's vertical, that's horizontal. So what does this look like? Well, my triangle is the same in both cases, but now I'd graph my line of reflection. Big Ideas will ask you to do that more often than not. They'll ask you to graph your line of reflection. Just be careful with that. And so here's what it would look like in our solution sheet. There's a vertical line. Notice it passes through our actual object, like we see here, passes through the object. That's why thinking of it in terms of a mirror can be confusing to some people, because you always think of it in terms of a mirror being a physical object. And so occupying the same space as some other object is a little mind-bending. So line of reflection is a little more appropriate. But here's our x equals 3 line of reflection. And simply put, you're just saying, all right, well, point A, how far away is it from the mirror? It's 2 units away, so I'm just going to continue down that line to the other side. 2 units to the other side, there's my image, a prime. Just be careful with labeling your primes. Okay, you'll do the same thing, just work your way around the triangle. And yes, it can be confusing, particularly when the line of reflection passes through your object, but just keep trusting the process. All right, there's point B. How far away is it from the line of reflection? 2 units away. Go 2 units to the opposite side. There's B prime. C is only 1 unit away, so 1 unit to the other side, C prime. Right, and so that in orange right here, A prime, B prime, C prime, there's our image after the reflection over that mirror. And once it's done, it actually kind of makes sense. You're like, oh yeah, I guess I can see it's reflected over itself. Even though it's a little jumbled here, it's a little more easy to understand. In our second example, there's a reason why we did it this way, but let's again work through it. Trust your process. First, graph your line of reflection. This one's a horizontal line at positive 1. There's our line of reflection. There's our original triangle. And again, just work your way around. Now, the difference is now I'm just counting vertically. So there's point A. How far away is it from the mirror? It's 2 units away, 2 units down. Now puts me on the other side. There's A prime. B is 1 unit away, 1 unit to the other side, B prime. Now here's an interesting thing that happens here. C is on the line of reflection. How far away is it from the line of reflection? It's 0 away, so C prime doesn't move. C and C prime are the same exact thing. And that makes sense because, again, this is that thing like if you were to go to your bathroom mirror and touch the mirror, it would look like your reflection was actually touching your same spot, like that finger or the hand or whatever it might be. It's because it's just matching that distance away. And so it makes sense that that would happen there. Just like over here, it wasn't one of the points or one of the corners, the vertices, but it was part of the actual triangle itself. Okay, so again, just trust the process, and you're just finding distance away and matching the distance to the other side. If there is no distance away, then that image point is just the same exact point. All right, our last problem, just going through this really quickly, was a composition. Again, the trick here, just like in section 1, is to do it in the correct order. Here you're given a translation and a reflection. So the first thing to do is you have some original triangle. In this case, it moves 6 to the left, 0 up or down. So I'd move 6 to the left. There's A prime, B prime, C prime. Now reflection over the x-axis, that is this axis right here. That's the y equals 0. Count the distance away, and you have your triangle.